Okay, so as we saw in the last example that we just did, if we're given the graph of the derivative, as we were in this example, there's a lot that we can figure out about the function, right? Not everything, but we can figure out quite a bit. And so this table here is actually summarizing the things that we know if we're given say the derivative or the second derivative or the function itself. So these are relationships between these three objects, right, or these three functions. So how you should read this is, for instance, if we focus on this line here, notice that we have on the left, it says increasing. I'll use a different color for this. So increasing corresponds to f prime being positive. So we know that that's a relationship between f and f prime, that if f is increasing, then the derivative is positive. If it is decreasing, then, or maybe I'll just use a different color again. If it is decreasing, then the derivative is negative, right? And then if it is flat, it's 0. So wherever it appears in this list, these things correspond, right? So you can match them up like that. So flat corresponds to 0. Okay, and so if we look at the next line and say maybe focus on concave up, that means that the second derivative is positive. So we can go all the way to the other end of the table and we get that relationship there. So there's a lot of relationships, as you can see, between these things. And one thing that I'll point out is that when it refers to straight here, you can kind of think of this the way that we talk about a function being flat, right? So we said that a function was flat when the derivative is equal to 0 or it has a horizontal tangent. So straight, what we mean by that is that the function is neither concave up nor concave down. And that's how you should think of it. So this could happen at a single point, or it could happen on an interval. If it does happen on an interval, so this is related to a question that was on the worksheet from last class. If you have a function that's neither concave up nor concave down, let's say on the whole real line, then it actually has to be a line, because, and it shouldn't have a little, okay, a straight line like this. Any straight line is going to have that property. It's neither concave up nor concave down. And if you have any other type of function, it will have some kind of curvature to it, right? So in that case, it will either have to be concave up or concave down somewhere, right? So this is the only type of function. So linear functions are the only type that are neither concave up nor down. So that is the answer to that question that I asked on the last handout. Okay, so here we have an example, and so we're given this graph, and suppose this is the graph of the second derivative of some function f. Okay. Right, and so if we think about this, given this function, what information do we have about the original function, right? So if we know that this is the second derivative, then everywhere that this function is positive, so here and here, we know that the original function is concave up. So I'll put this over here. Okay, so we know that f is going to be concave up on -7 to up to -2. Then the second derivative is equal to 0 at 2, so it's not concave up at that particular point, and then afterwards it is still concave up. So, and from -2 to 5, right? And then also f will be concave down on the interval -infinity, so up to minus, oh sorry, not 8, 7, up to -7, down, concave down on that interval, and from 5 to infinity. Okay, assuming that this graph keeps going in the direction that it looks like it's going. Okay, so those are the two things that we can tell from this. Also, we know that at 7, since it switches, so it is concave down on -infinity to -7, and then switches to concave up on -7 to -2, we get an inflection point at x equals -7. And then the same thing, well, not exactly the same, because the function will flip from being concave up to concave down, but it also flips at x equals, or that's not minus, at x equals 5. And at x equals 5. So we know the x coordinates of the inflection point. We don't know what the function value will actually be. We can't tell that from the graph of the second derivative. And so, yeah. Another thing that we could say is that on the intervals where this is positive, so from -7 to -2 and -2 to 5, we know that the derivative is increasing, and so that's so where it's positive, the derivative is increasing and the function is concave up, right? So that's what we could read off of this chart. So it's convenient to have this, but it can be hard to look at, I know. So I would suggest looking at a particular problem like this example and then maybe checking this chart to see if it can help you figure out what's going on. But yeah, I think it's good to see it all in one place. So don't forget to do the comprehension check. All right.